Hello, everybody. So today I'll talk about the calculus of variations, section 1.3 to 1.4. So for today, I'll first prove 4 lemmas, and then I will use them to prove our final result, which is the Euler Lagrange equation. So now, without further ado, let's get started. So the first lemma is a pretty basic one. It states basically if we have alpha x as a continuous function on the interval ab, and if for any h inside the space of continuous function on ab with ha and hb equal to 0, we have that the integral of alpha times h is 0, then alpha would necessarily be 0, right? This is pretty intuitive. But how to prove how to put it in a rigorous statement? We can use a proof by contradiction. So let's do proof, and I'm going to assume that there exists a point inside AB, so call it C, such that alpha C is not 0, and we can assume that that point is positive, right? So assume that there is such a point. All right, and then what do? We should use the continuity condition, right? So what does that mean, right? That means for any 0 less than epsilon less than alpha c, there exists a delta greater than 0, such that, so I want to bond alpha from below on an interval, okay? So such that alpha x is greater than alpha c, greater or equal, that's both fine, okay? So greater or equal to alpha c minus epsilon. So this side will still be positive, right? And I want that to happen on the interval c minus alpha, c minus delta, c plus delta. Of course, this has to be inside the bound of AB, okay? And so now what I do? Now I want to define a function h such that h satisfies this condition. H is in CAB and also HA equal to HB equal to 0. So now we define an h, okay? So define h as follows. So h equals, so now I'm gonna basically create like a head function on the interval c minus delta, c plus delta, okay? And then I'll do the integration. So how do I do this? I will basically have hx equal to 0 if x is not inside this c minus delta, c plus delta. And here I'll have what? I'll have x minus this left point, which is c plus delta here, right? And that multiply with this right point minus x. Okay, so c plus delta minus x. So what is this gonna look like, right? It's gonna look like something like a quadratic function that's upside down, right? And this is obviously continuous, right? So we're gonna use this. So this is on the interval AB, okay? And then what do? We basically perform the integration, right? Then the integral from a to b of x, hx dx. Now notice that h is only non-zero on this interval, right? On this interval. So then I can only I can just perform the integration from this c minus delta, c plus delta of alpha x times hx. But this is bounded from below by by this value, right? So alpha is bounded from below by this value. So we can have basically taking the constant out, which is going to be this, times the integration from c minus delta to c plus delta of hx. And that's obviously positive because this quantity is positive and this quantity is obviously non-zero and positive. Okay, and now this is proven, right? Because this is a contradiction. So this is a contradiction. All right, so this is fairly simple. Now let's continue to our next proof. So the next lemma is stated as following. We have the same condition that alpha x is continuous on AB. And also, we also have that for any h inside the space of C1 AB with HA and HB having zero boundary, then this following integral is always zero. The integration of alpha and h prime is always zero. If this is satisfied, then alpha is a constant on the interval AB. So one observation here, right, is that so if we have the condition that alpha is also C1, so if alpha is differentiable, then here we can basically apply the integration by parts, right? And then that would basically state that alpha prime times h dx equal to 0, and then you can basically apply this previous lemma, which is pretty obvious. But then we don't have that condition, so so we have to sort out a different proof. So how do we do this? We do it by explicitly constructing a constant that should equal to alpha. So let's prove. Let C inside R be such that, so I want C to have the following property, that the integration of alpha t, or actually I'll just use alpha x minus C from A to B, this should equal to 0. So that is easy to find, right? Just let C equal to this 1 over b minus a of the integration from A to B of alpha x dx, right? So C can be found by this value. Then what do we do? We now construct a specific h prime. Okay, so also let h be defined as the following. So let h be defined as the integration from a to x of this function of alpha t minus c dt. All right, so an observation here is that h is actually c1, right? Why? Because the integrand here is continuous because this alpha x, this alpha t is continuous, and c is a constant, so also continuous, and also and then the integration is obviously differentiable, and the derivative is continuous, so h is c1. So h is inside c1 ab. Also, this is also satisfying. Okay, ha equal to hb equal to 0. Why is that? Easy to observe, right? Because if you replace this x by a, obviously h is 0. That's so obvious, right? If you replace this x by b, then also this implies this, right? So this is satisfied. So h is a function that satisfies our requirements, and then we're going to apply this, right? So now we're going to use the following integration. Okay, so we're going to integrate from a to b of the function alpha x minus c, this times h prime. Okay, so what does this equal? We can take apart these two, and this would equal to the integration from a to b of alpha x times h prime x dx, and also minus c times the integration of h prime, which is basically hb minus ha. And this is easily observed to be 0, right? Because this is 0 by this condition. And these two endpoints are 0, so this is also 0. So the whole thing is 0. But then also, the integration from a to b of this formula is basically what is basically alpha x minus c times h prime. This equals the integration from a to b of alpha x minus c squared dx. And that equal to 0. That implies alpha x equal to c, right? And the reasoning is basically the same reasoning as in our previous proof. All right, so now let's move on to the third lemma. Okay, it states that if alpha is continuous on AB, and if the integration of alpha with h double prime is 0 for any h of the class C2, and also all the boundaries are 0, then we would have some constant C0 and C1 such that alpha would equal to this linear function. So the way of proving this theorem is basically the same idea as the last one. So we're going to construct this C0 and C1 explicitly. So let's do that. Let C0 and C1 be such that the integration from a to b of the function alpha x minus C0 minus C1x is equal to 0. But then that's not sufficient to determine two variables, right? So we would also have the following condition, that basically the integration from a to b of the function, the integration from a to t of alpha t minus C0 minus C1t dt. So that's a function of the integration of this function with respect to dx. This would also equal to 0. So what does this mean, right? This basically defines a linear system to determine C0 and C1. And you can actually write this out in a matrix form. And if you actually do that and you find the determinant, you can actually factor it and see that the determinant is always non-zero if given that a and b are both positive and a is strictly less than b. And that can always be arranged, right? You can always translate this alpha to a positive integral, and then you can find the C0 and C1, and then prove this theorem. And then once after finding this C0 and C1, what do? We basically use the trick as in the last lemma. So we're going to integrate from a to b of the function alpha x minus C0 minus C1x times h double prime x dx. And this would equal to what? You can just distribute again, right? So this is from integration of a to b of alpha x times h double prime x dx, and then minus C0 times the integration of a to b of h double prime, and then minus C1 times the integration of from a to b x times h double prime dx, right? And then you can observe that these two terms are all 0. Why? Because this is given by that condition. And this is basically C0 times h prime b minus h prime a, and those are all 0, so that's fine. And the last term is also 0. Why is that? Because we can basically check by integration by parts, right? So these are all 0. Why? Because we basically find this integral. This would equal to what? This would equal to x times h from a to b, right? And minus the integration from a to b of h prime dx, right? Because you differentiate in terms of x, then x is gone. So that's the result. And that would equal to that would equal to basically h times, sorry, that equals to b times h b minus a times h a, and that's 0, and this part is obviously also 0, right? Because that's minus h b minus h a. Okay, so that's 0. So now this is 0, but also observe this equation is basically alpha x minus c naught minus c1 x squared, right? That means this equation is actually 0. And the same reason as above, right? So we would have alpha x equal to c naught plus c1 x, and that is proven. Actually, sorry about that. Just messed this up. There's actually prime here, okay? Right? And now this is right. So, all right. So now let's continue to the most important lemma in our section, which involves two functions, alpha and beta, and they're all continuous on the interval AB. And we require the condition that for all h in the space C1 with 0 boundaries, this integral is 0. So the integration of alpha times h plus beta times h prime is 0 from a to b. Then the result is that b would actually be continuously differentiable, and b prime would equal to alpha on AB. So the emphasis here is that we previously don't know that if b is differentiable. Okay, so b is not required to be differentiable as a start, but by the end, we will prove that it's actually differentiable and the derivative equals to alpha. So now let's prove this. We start by using the same kind of trick. We define a new function here. Define ax to be equal to the integration from a to x of the function alpha, and then observe that your function a is actually in the space C1. Why? Because it has a derivative of alpha, which is continuous, right? So then we can take care of this part and rewrite it as something else. Then the integration of from a to b alpha x hx dx, this would equal to what? This would actually equal to the integration of a prime x hx dx. And then now we use the trick of integration by parts again, right? So this would equal to the value b minus a, and there will be a subtract the integration from a to b of a x h prime x dx, right? And this is obviously 0. Why? Because the boundaries has turned value of 0, and then now we plug into this equation again. So the integration of from a to b alpha x hx plus beta x h prime x dx now would equal to the integration from a to b of beta x minus a x times h prime x dx, and this would equal to 0, right? Because we stipulated that this would always equal to 0 for any h. Then what do we get? Then apply lemma 2. Then we would have that this beta x minus ax would be a constant. So there exists a c such that beta x minus ax equal to c, right? That's basically by this lemma. So the function is a constant. So this function is a constant here. And then we differentiate both sides, and then we will get beta prime x minus alpha x equal to 0. Hence, beta prime x would equal to alpha x. All right. So that proves the theorem. And now let's move on to section 1.4. And so prior to talking about our main results, which is the Euler Lagrange equation, I would like to first state a version of Taylor's theorem, just to ensure that we're all on the same page of what I meant by Taylor's theorem. So Taylor theorem, let f be a m times continuously differentiable function defined on an open set E inside Rn. And now let's just pick a point A inside E and also an open ball of radius r centered at A that's contained in E for some r greater than 0. Then we can now say that for any h inside the ball of radius r centered at 0, then obviously a plus h is inside the set, the ball of radius r centered at A. And the function at that point can be estimated by the following equation. That is basically the Taylor polynomial, and then plus an error term. And this error term is quite important, that it has the feature that the error term at h divided by the norm of h to the power m will converge to 0 as the norm of h converges to 0. And this will be important later on in our error term for the functional. So with that clarified, let's move on to the Euler Lagrange equation. So this is the main theorem in our section. So so first, let f be a function of class C1 defined on the space R3. And then we're going to denote this by U. So U is the set of all functions y inside C1AB with the condition, with the boundary condition that YA is equal to capital A and YB is equal to capital B. And we're going to equip this set with the norm of the C1 norm. So this is actually a subset of our vector space C1AB, right? The norm vector space. But this is not in general a subspace because of this condition. So now let's define the functional on the space C1AB, and it is defined by this jy would equal to the integration from a to b of this f, taking the points x, y, and y prime. And then if suppose that j has an extremum at some point y inside V, so this is an extremum in V, not in general in C1, because in C1 there will be more requirements, but we're restricting ourselves to the subset V. So if y is an extremum for j, then y must satisfy the following equation. That's basically the partial derivative of f with respect to y minus ddx of the partial derivative of f with respect to y prime would equal to 0. So a remark here, okay, is that fy is in general a function of x, y, and y prime, right? And so is this fy prime. But what does this ddx mean here? Because y and y prime are essentially a function of x, right? So this is basically defining a ordinary differential equation of degree 2, right? So the highest term could be y double prime because you have this ddx here. And then, so we're basically saying that if y is an extreme, then y must satisfy this ODE. So basically, this would be a necessary condition for an extremum. And this is actually not too hard to prove with our previous constructs. So let's go about proving it. So first I'm going to try to find the principal linear part of J. All right, so let's first define this delta J. So delta J at Y applied to a function H inside our space C1AB. This is defined to be what? This is defined to be J of Y plus H minus J of Y, right? This is as in our last video. And now let's write this in terms of the integration. So this would equal to what? This would equal to the integral of from a to b of f applied to x, and then this y plus h, right? So y plus h, and then y prime plus h prime dx, and minus the original, right? So f x y prime dx. And then now we do is that we pull them into one integral, right? So this equal to from a to b of f x y plus h y prime plus h prime minus f x y prime dx. And now here we would now apply our Taylor theorem. Okay. So what does that equal? That equals so we first the derivative in terms of x is not needed because there's no change in value here, right? So it's only the the second and third term. So that would equal to fy times h plus fy prime times h prime plus some r of h prime dx. And now we can see that this is obviously linear, a linear functional, right? So this is the linear part. And now plus, for this part, let's do a little bit of a estimation. So how do we estimate? Let's estimate it by the C1 norm of h. All right. And then we can observe that this part, we have always h, the C1 norm, is defined to be the maximum of h plus the maximum of h prime. That is on the interval AB. That is always larger or equal to the following quantity, which is h squared plus h prime squared a half, which is, this is the R2 norm of this of the vector h prime, right? So this is the norm that we're using in here, right? So my point is, so as the C1 norm of h go to 0, we have the integration from a to b of r h prime divided by hc1 dx. This is going to go to 0. So this, so epsilon would equal to the integration from a to b of r h prime hc1, and the principal linear part here is delta jh would equal to the integration of a to b of fy times h plus fy prime times h prime dx. Okay. So again, this corresponds to the notion of delta j h equals to this lowercase delta jh plus epsilon times hc1, or the norm of the vector space, which is, in our case, is the C1 norm. So then recall that we proved this theorem that basically said that if the functional is differentiable and the functional achieves the extremum at the point y, then the first variation must vanish at that point. So then we must have delta JH equal to 0 for any H. But then this H is the difference of some Y tilde and Y inside the set V, okay? So such that H equals to Y tilde minus Y with Y tilde also in the space V. Then we look at this integral, right? That basically states that the integration from A to B of Fy times H plus Fy prime times H prime dx equal to 0 for any H inside the space C1AB. But then H is a difference of Y tilde and Y. So that implies HA equal to HB equal to 0, right? Because Y tilde and Y, they have the same boundary values of capital A and capital B, right? So we have this equation. But then observe that we can just simply apply the fourth lemma, right? Which is this, right? If alpha beta are continuous and this requirement is satisfied, then beta would also be C1, and then beta prime would equal to alpha. So in here, our Fy and Fy prime are continuous, right? Because F is C1, so its derivative is continuous. So by lemma 4, that would imply that. So basically, that would basically imply our last result. So Fy minus ddx Fy prime equals 0. So notice this actually takes Fy and Fy prime as a function of x, but that's okay because Fy and Fy prime is a function of x, y, and y prime, which is then a function of x, right? So then we're done. So just to recap a little, we first find the principal linear part of our functional delta j, and we show that it is equal to the integration of Fy times h plus Fy prime times h prime. And then we applied the theorem from last time, basically says that the first variation must be 0 because y is an extremum. And that is for any h being the difference of y prime, y tilde and y inside the space V. But then that satisfies our requirement of lemma 4, which is basically h is C1 and h is 0 on the two boundary points. And then we just apply lemma 4, and then that gives us the final results, which is the Euler Lagrange equation. And that is a necessary condition for an extremum. So yeah, then we're done today. I hope you enjoyed the video. See you next time.